Hello everyone, my name is Devra Tomar and today I will be presenting to you our work on self-supervised generative style transfer for one-shot medical image segmentation. Automated medical image segmentation is crucial for diagnosis and planning. CNNs have achieved state-of-the-art performance in the field of image segmentation, but they need a lot of labeled images, which is either not feasible or is too expensive, especially from multiple sites. Also, pre-trained deep networks often fail to generalize to new test data if it's not distributed identically to the training data. Performing hand-tuned data augmentation or adaptation only provides suboptimal solutions. Thus, few-shot or self-supervised learning-based approaches are crucial in such scenarios. Among such approaches, atlas-based methods have gained popularity in the research field. In these methods, an atlas is used to register each image and warp one onto another, where the segmentation also undergoes similar warping operation. However, heterogeneity incurred due to different scanner properties or anatomy causes inaccurate warping and erroneous segmentations. In this work, we focus on learning the style or heterogeneity of unlabeled target images in a self-supervised way, followed by learning warping fields that can be used to synthesize novel image segmentation pairs from a single labeled base atlas image. Our approach is generative in nature. This implies we can generate infinite synthetic data by just sampling from Gaussian noise. Our approach allows different hospitals to just share the generative models instead of the real patient images for training a CNN. We can use the synthetic images to train a CNN in the target style-like environment. Previous methods trained the spatial and appearance models separately, resulting in suboptimal solutions compared to joint optimization of all modules. In summary, our method formulates the synthesis of novel volumetric images and their corresponding segmentation labels as a learned random spatial and style deformation of the given single labeled base atlas image from a latent space. We employ a style encoder that learns to cluster similar style images together in a self-supervised manner while imposing normal distribution prior on the latent style codes. The appearance model is trained simultaneously to generate different styles of the base image without changing its spatial structure. The flow model then learns to register target style base image onto the target image. Since the style of the two volumes being registered is the same, our method does not suffer from inaccurate warping effects. Now we briefly focus on the individual components of our framework. We train style encoder using the proposed self-supervised volumetric contrastive loss. We adapt MoCo for volumetric medical images to cluster image style as opposed to the original classification task. Also, we generate positive keys using a learned spatial transformation instead of standard augmentations like random cropping in the original formulation. During training, we sample a query image and get a style code Q using style encoder, while the positive key style code K plus is obtained from a key style encoder, which is a moving average momentum updated copy of the style encoder. The negative keys are kept as a separate queue, which gets updated after each training step. Here we show the 2D Disney projection of learned style codes confirming that images with similar styles are indeed clustered together. Appearance model is responsible for translating the style of the source image S to that of the target image T, given its style latent code as predicted by the style encoder. We use two loss terms that helps in the convergence of appearance model. First is style consistency loss that guides the appearance model to generate images with the same spatial structure as the source image but with a different style in a consistent cyclic manner. Secondly, style identity loss enforces the appearance model to generate same image using its own style. Our flow model builds upon a spatial transformer network F that warps a moving target style source image to the fixed target image. The spatial transformer F generates a correspondence map called flow field, which is used to register the target style source image onto the target image. In summary, we use the following laws to train our flow model for generating smooth flow fields. Once appearance and flow models are trained, we map the flow fields with respect to the labeled base image for different unlabeled target images and map them onto a normally distributed latent space called flow latent space via adversarial autoencoder loss. During data generation phase, the appearance model learns to map the normally distributed style latent code onto a novel style of the labeled images, whereas flow decoder learns to generate novel realistic deformations of the base image, which is used to warp the style base image and its segmentation. Thus, we can synthesize new image segmentation pair by simply sampling noise from Gaussian distribution. We then use these synthetic images to train a separate 3D unit. We achieve SOTA one-shot segmentation performance on Candy and OSS datasets when compared to other baselines. Here, we compare the qualitative segmentation results of our method with other baselines. Our framework achieves results very close to the fully supervised CNN using just a single label atlas. We did some ablations to see the effect of various components of our method. We see that excluding appearance model loss terms degrades the registration accuracy as well as the supervised segmentation accuracy of UNet trained on the synthetic image segmentation pairs. We also observe that joint training of all modules results in better performance as compared to training them separately. To evaluate the appearance model's efficacy in generating the unlabeled target dataset styles, we experimented with replacing the appearance model trained on Candy with the one trained on OSS and vice versa to generate images in the style of the target domain. The domain gap between the two data sites would severely impede the generalization ability of the trained supervised model on the source data site, while performing style adaptation between OSS and Candy datasets provides substantial improvements. We also observed that segmentation performance improves as we use more synthetic image segmentation pairs to train the 3D unit. Here we present some examples of the synthetic images generated by manipulating style and flow codes. Along the row, only the style of the image changes, while along the column, only the shape of the volume changes.